This is a video. You can pause it and rewind or play it at 1.5 speed if you'd like to make things work the speed you're ready for. The first topic of the year was energy, and most specifically we learned about the law of conservation of energy, which states that energy cannot be created or destroyed. The first analogy we looked at this year was the Feynman lecture, the boy and his blocks. And a boy had 28 blocks. He'd play with them in a variety of ways. But at the end of every day, the mom would want to count the total number of blocks. As time goes on, she figured out that she could count blocks that were in front of her and even ones she couldn't see, suggesting that there's ways to account for amounts of energy, even though energy is not easy to see. We then came up with some energy storage accounts, or certain ways that we can account for the amount of energy and store it in a variety of counts. And we listed some energy storage accounts. By the way, the last one down here talks about energy bar pie charts. We used energy bar graphs instead to show how energy might change when looking at a specific system. On the bottom of side 1 of the review, there's some questions down here that I thought would be helpful to look at before we solve the problems. Number 3, what is a closed or isolated system? It's a system that does not allow any energy in or out of the system, versus an open system which does allow energy in or out of a system. All the systems we considered this fall were closed systems. The total amount of energy in the system remained the same. We stated again the law of conservation of energy states that energy cannot be created nor destroyed. Here are some energy storage accounts that we decide. Energy stored as motion, we said, would be kinetic energy. Energy stored in the vertical height, GH. IT, or vertical position of an object. The higher it is, more gravitational energy it has. Elastic energy can be stored in the shape of an object. If you change its shape, and it has a tendency to go back to its original shape, like stretching a spring or a rubber band. Chemical energy can be stored in the chemical bonds of certain molecules and substances, which can be released by burning or going through other types of chemical reactions. And then thermal energy most commonly is due to an increase in temperature due to friction, but it could also you could have increases in thermal energy due to light or sound. We generally assume that the thermal energy in the first snapshot of each situation we're going to look at is 0, but the other accounts we can consider what we would like to make the 0 reference or minimum amount for. Since we're down here, we'll go ahead and talk about the 3 energy transfer mechanisms. We said you could heat an object by putting a warmer thing next to a cooler thing. An object could experience an increase in energy due to radiating, which would be exposure of electromagnetic waves like sunlight or microwaves. And you can then physically work something, like if you think about a piece of clay when you were in elementary school, as you pushed on it over and over and over, the temperature would increase and became more pliable. How about some energy bar graph problems that we can consider? Here's the one at the top of the page. We've got a wind-up toy. It says a wind-up toy is wound up, then walks across the table and comes to a stop. We can see that the images below the bunny, we've got a long arrow suggesting it's moving fast, a shorter arrow suggesting it's moving slower, and the dot representing it's stopped. We want to always define our system with a dotted line and with words. We're going to say in this system that the bunny is part of our system, and then we'll need to include the surface and the surroundings because of increase in temperature. Surface, I wrote surface twice, and surroundings. Looks like we're blocking the light that way, so let's maybe tilt it this way. This might be better. So then we want to consider what things change, because we only need to include what changes of the energy here. We already mentioned that the speed of the bunny changes. In that count, that'll fall in as kinetic energy, and that's going to decrease. The shape of the spring, we said that it's fully wound up, so the spring's already stretched out, ready to go, storing that energy. As it goes across the table, the amount of elastic energy will decrease, and then the temperature of both the bunny and the surface will increase. The sound waves that bounce into the air, into the surrounding areas, will increase the temperature as it vibrates things like blinds and walls and other things that are in the room. So the thermal energy will increase. So taking a look at this, we're going to start with some kinetic energy and some elastic energy. we'll try to keep the order of these storage accounts the same as we go across. So start with kinetic, then elastic, and finally thermal energy. So how many bars do we want to start with? The number of bars we choose is somewhat arbitrary for the first one as long as it allows for us to make the changes that we have. So we could start with, say, 4 bars of kinetic energy and 4 bars of elastic energy because it's moving fast and the spring is fully wound. Sometime later there's going to be less kinetic energy. Maybe we could go with 2 bars of kinetic and 2 bars of elastic. Well, what about the other 4 bars that were there? We'd have to have those jump into thermal energy, which there's 4. 1, 2, 3, 4, which is a total of 8 again. At the end, is there any kinetic energy? Nope. Is there any elastic energy? We went from 4 to 2. Nope. So there'd all be thermal energy. Well, there's only 6 bars here, but I started with 8. What am I going to do? Well, there's 6. Then I can just build 2 more on top of here if I need to. This also would have worked easily if we would have done 2, 2, and then 1, 1, and 2, and then just a total of 4 here. Either way, you could have the same amount of energy bars for each of the 3 bar graphs, so the total amount of energy in the system does not change. Let's do 1 more of these and we'll take a break for energy. So this is one of the problems that we did together in class earlier this year. It's important to read the problem. The baseball is thrown into the air and then falls back down. Place that represents the speed and direction next to the ball. So the ball is going really fast at time 0. It's going pretty slowly when it's close to the top. At the top it's stopped. It's kind of going an in-between speed at D. And actually the speed at the end would actually be the same speed